Alright, we're doing a mass transfer problem. We've got a lead tank of diameter D and height H. So let's draw this tank. And so this diameter is D and the height is H. And it's full of stirred water, H2O. The lead from both the sides and the bottom of the tank slowly dissolves into the water. So we've got lead coming in from here, PB, and coming from the bottom. And it's controlled by convective mass transfer at the lead-water interface. The water is initially lead-free, so this is one of our boundary conditions. Well, it's our initial condition. Give an equation which can be integrated to give the concentration of lead in the water as a function of its dependent variables. So, would we use fix and continuity for this problem? No, we would not, because we have convective mass transfer. We're going to do a mass balance. And so what's really happening here? We've got lead moving from the sides into the tank, and we've got the concentration of lead in the tank changing. So let's equate these two things. The rate of lead moving into the tank equals the change in amount of lead in the tank with time. So how do we actually represent these? Well, the rate of lead moving into the tank is the flux of lead is species A, times the surface area, and that equals the change in the amount, and the amount is going to be the concentration times the volume with time. Because we have convective mass transfer, Na is going to be KL times CAS, Ca at the surface, minus Ca inside the tank. The area of the surface, or the surface area, is the bottom of the tank, which is pi d squared over 4, plus the walls of the tank, because it says that the lead from both the sides and the bottom of the tank slowly dissolve into the water. So we've got the bottom of the tank, and now we have the sides, which is pi dh. And that equals the volume of the tank. So the volume is going to equal pi d squared over 4 times the height. And none of that is changing with time. And so the change in the amount of lead in the tank is pi d squared over 4 times the height times dCA dt. And you could stop at this point, or you can combine. So we've got KL times pi d squared over 4 plus pi dh over pi d squared over 4 times h dt equals dCA, Ca at the surface minus Ca. That's our equation. Our boundary condition, or our initial condition, is T equals 0, the concentration in the tank equals 0, and then finally at T equals some time, T, Ca equals the final concentration. And some assumptions are constant temperature and pressure. Note that there is a problem on Welty, Wicks, Wilson, and Rohrer on page 589 that has the same type of setup, but it has a different surface area. So you can look here for a similar problem. And this is an unsteady state problem.